Welcome back to the deep dive. We are jumping straight into the deep end today. We're tackling a subject that's, well, famously tricky, quantum mechanics.
Yeah, it has that reputation. But our mission here, based on these foundational guides we've been looking at, isn't really to master it all. It's more about pulling out what you might call the theoretical minimum.
Right, the absolute core ideas you need to understand why it's so different from the classical physics we see around us.
Exactly. We want to get at the logical shift, the mathematical shift that makes the quantum world, well, quantum.
And I think that's the crucial starting point people miss. The idea that classical mechanics and, physics of billiard balls, planets, all that, it's not actually fundamental.
It's just an approximation, a really, really good one for big things, but still an approximation of QM. It breaks down at the small scale.
So the real challenge isn't necessarily the math itself, although that can get complex. It's the fundamental logic changing.
That's it. Classical logic is built on sets. Things are either true or false, heads or tails. An object is here or it's there. Very definite.
Black and white.
Pretty much.
Yeah.
QM, though, it just sort of throws that out. It replaces those simple sets with these abstract mathematical spaces, complex vector spaces.
Vector spaces, okay. So not just simple categories anymore.
Right. And in these spaces, a quantum system can exist in, well, potentially infinite combinations of states between true and false or heads and tails. It's inherently probabilistic. That's why we need the vectors, the geometry, to describe it.
That leap from a definite spot to a probabilistic vector, that's huge. And to make it less abstract, the simple system everyone starts with is the two-state system. Right?
Exactly. Classically, a two-state system is like a coin flip, heads or tails. Honestly, pretty boring. But quantum mechanically, that same simple idea becomes the spin of a particle, like an electron, up or down. We call it a qubit, and it's like way more interesting. It's the foundation for quantum computing.
Okay, so the qubit, that's where the new quantum rules really start to bite.
Yes. Rule number one is about the state itself.
So classically, the state is just like its position and momentum, a point on a map, maybe? What's the quantum equivalent?
The quantum state is this vector. We write it as design wrangle, and it lives in that complex vector space technically, a Hilbert space. Now, this vector represents everything you can possibly know about how the system was prepared.
Okay, maximum possible knowledge. That sounds definite.
But here's the kicker. Maximum knowledge in QM isn't definite prediction. It's probabilistic.
Wait, hang on. So even if I know everything the theory allows me to know, I still can't say for sure what will happen in a measurement.
Precisely. The state vector gives you probability amplitudes. These are complex numbers. You have to square their magnitude, their size, to get the actual probability of measuring a certain outcome.
Complex numbers. That's why the I, the imaginary unit, pops up everywhere in QM, isn't it? It's not just a mathematical trick.
Not at all. It's fundamental. Those complex amplitudes carry phase information, which is crucial for interference. Like waves interfering in the double slit experiment. It allows for superposition, where things can be in multiple states at once, effectively.
Okay, so state is a complex vector holding probabilities. What about the things we actually measure, like position or energy or that spin we talked about?
Those physical observables, the things you can actually put a number on in an experiment, they correspond to mathematical operators. Specifically, Hermitian linear operators. Let's call $1.
Hermitian. Why is Hermitian? That sounds like a very specific mathematical constraint.
It is, but it's absolutely essential. Think about it. If you measure, say, the energy of something, the result you get has to be a real number, right? You read volts or joules off a meter. You don't get 5 plus 3i joules.
Right, okay. Needs to be a real-world number.
Exactly. And the mathematical property of being Hermitian guarantees that the possible results of the measurement, the eigenvalues of the operator doll, are always real numbers. It connects the abstract math to physical reality.
Yeah.
Non-negotiable.
That makes sense. It anchors the theory. So we use this operator dollar for a measurement. What results can we get?
That brings us to principle 2. The only possible outcomes you can ever measure are the specific eigenvalues of that operator. Call them lambda. Nothing else is possible.
Eigenvalues. Those are like the special values associated with the operator.
Yeah. Think of them as the allowed results, the quantized values. And if the system happens to be perfectly prepared in a state corresponding to one specific eigenvalue, we call that an eigenstate, lambda wrangle, then the measurement is guaranteed to give you that eigenvalue, lambda.
But that's the special case. Usually the system is in some general state, generally a mix, a superposition.
Correct. And in that general case, when you measure a dollar, you'll get one of the eigenvalues, lambda, but which one you get is probabilistic. If you do the experiment many times on identical systems, you'll get a distribution of results.
And the average of those results over many trials,
Yeah.
that's the expectation value, Langle, angle, ergo.
That's it. And the math gives us a neat way to calculate that average directly from the state and the operator. It's that inner product sandwich notation, Langle-Wrangle.
Okay. The
Yeah.
Langle-Sire-Wrangle. That formula tells you the average outcome you'd expect.
It essentially weighs each possible eigenvalue outcome by its probability, given the state psi-wrangle.
So we have states as vectors, observables as operators, outcomes as eigenvalues. But what does the act of measuring actually do to the state? This is where things get really weird compared to classical physics, isn't it? The idea of just gently looking at something.
Completely breaks down.
Yeah.
Classically, we assume observation can be passive. I measure the length of my desk. The desk doesn't suddenly change its weight because I measured its length.
Right.
In QM, any interaction strong enough to get information about one property, let's say, position is inevitably strong enough to disturb another property, like momentum. Observation is invasive.
You can't just peek without consequences.
Exactly. Let's use the spin example again. Say, spin along the z-axis, sigma's Villa, and spin along the x-axis, sigma. Imagine you prepare a particle very carefully. So its spin is definitely up along z. So sigma is plus 11, guaranteed.
Okay.
If you measure sigmas again right away, you'll just confirm it. You get plus 1, no surprise.
But now we do something in between.
Right. Suppose, after preparing it in the sigma spindle state, you decide to measure the spin along the x-axis. What happens? Well, you get a result, either plus 11.1 or $1 for the x spin, each with 50% probability. The measurement forces the state to choose an x direction.
And the original z information.
Mon. Poof. If you immediately measure sigmas again after measuring sigmas, the outcome for sigma zillas is now completely random. 50% chance of plus 1, 50% chance of getting 1. The act of measuring 6 spellers totally randomized the z-spin.
Wow. So measuring one property actively destroys the information you had about another incompatible property. You just can't know both precisely at the same time.
You can't. And this isn't just a limit on our instruments. It's fundamental. It leads straight to the uncertainty principle.
Which says this limitation is quantitative, right? There's a mathematical formula for how uncertain things have to be.
Yes, and it arises directly from the mathematics of the operators. This inability to know two things simultaneously happens when their corresponding operators don't commute.
Meaning the order matters. Applying operator A then B gives a different result than applying B then A. Like putting on your sock then your shoe is different from shoe then sock.
Huh. Good analogy. Mathematically, we write it as $1, B equal AB, BA. If that's not 0, they don't commute, and there's an uncertainty relation between them.
And the most famous example is position, $6, and momentum, Doppler.
The classic one. They absolutely do not commute. Their commutator is actually a fundamental constant of nature. $6, P equals I bar. That little I bar is like the mathematical signature of quantumness.
I'll be the imaginary unit and Lozia, Planck's constant. So the universe's fundamental graininess and its probabilistic nature are encoded right there.
Pretty much. And because $6 don't commute, there's a limit to how well you can know both. That's Heisenberg's famous relation. Delta x of these, delta p Jacobier.
The uncertainty in position times the uncertainty in momentum has to be greater than or equal to this tiny constant.
Right. So if you try to pin down the momentum of a particle really precisely, make delta p super small, then delta xt, the uncertainty in its position, has to become enormous to satisfy the inequality.
A particle with perfectly known momentum is, in a sense, spread out everywhere in the universe.
Its wave function is, yes, it has no definite location. It's counterintuitive, to say the least.
Okay, so states are vectors, measurements are invasive operators, and uncertainty is fundamental due to non-commuting properties. Now, we get to what the source material calls the essential fact, the thing that really separates quantum from classical: entanglement.
Entanglement. Yeah, this is where classical intuition completely crashes and burns. The quote emphasizes it's the thing that makes QM so different.
The classical intuition being, if I know everything about a whole system, I must know everything about its parts. Like if I fully scanned a car.
You'd know about the engine, the wheels, the doors, everything individually. Complete knowledge of the whole implies complete knowledge of the parts. Seems obvious, right?
Totally logical. How else could knowledge work?
Well, quantum mechanically, it doesn't work like that. Not always. Entanglement is this situation where you can have complete maximal knowledge of the combined system, say, two particles together, yet know absolutely nothing definitive about either particle individually.
Wait, Know everything about the pair, but nothing about each one on its own. That feels impossible.
It feels impossible classically, but it's how the quantum world operates. Mathematically, it means the state vector for the combined system can't be broken down or factored into separate independent state vectors for each particle.
They aren't just two particles existing near each other. Their fates are linked in the math.
Deeply linked. Their combined state is a single entity, even if you separate the particles by huge distances.
This sounds like the famous Alice and Bob scenario with their entangled particles.
Exactly, the standard example. Alice has one particle, Bob has another, far away. They were created together in an entangled state, let's say the singlet state.
Okay, the singlet state. What happens when Alice measures her particle's spin, say,
She gets a random result. 50% chance spin up, +1. 50% chance spin down, and that was 1. Totally unpredictable for her. Same for Bob. If he measures his particle's spin, tells his dill, he also gets a random +1 or =1.
Individually, just noise, but
when they later compare their results, they find a perfect anti-correlation. If Alice measured +1, Bob always measured -1. If she got -1, he always got +1. Their outcomes are intrinsically linked. Nagel, Cygnus tells us 1.
that instantaneous correlation, that's the spooky action at a distance Einstein was so worried about. How can Bob's particle know what Alice measured instantly, even light years away? Doesn't that violate relativity? No faster than light signals?
That's the million-dollar question, and it highlights a really subtle but crucial point. Entanglement involves correlation, incredibly strong correlation, but it does not allow for faster-than-light signaling or communication.
Okay, how does the math prevent that? How come Alice can't use this to send Bob an instant message?
It comes down to what Alice can actually observe locally on her end. Let's say Bob, over on his side, decides to do something to his particle. Maybe he rotates it using what's called a unitary operation. This is just a standard quantum evolution preserves probability.
Okay, Bob fiddles with his particle. Does Alice see anything change instantaneously?
No, absolutely not. All the information Alice can possibly get from her particle by doing any measurement she likes is contained in her local density matrix. Think of it as her local statistical summary.
Her probability dashboard.
Kind of, yeah. And the crucial point is, Bob's distant action, his unitary operation on his particle, does not change Alice's local density matrix at all. Her statistics remain exactly the same. Still 50-50 random outcomes for her spin measurement, for instance.
So, because her local measurement results look statistically identical whether Bob did something or not, she has no way of knowing if he did something. No message received.
Precisely. The correlation is real, it's deep, it's non-local in some sense, but you cannot use it to send information faster than light. The mathematical structure of QM rigorously upholds causality.
Goo. Okay, so let's try and pull this together for everyone listening. We started saying QM needs a whole new way of thinking, ditching classical ideas.
Right, and the minimum theoretical toolkit seems to involve accepting complex vectors for states, encoding probabilities, accepting Hermitian operators for physical measurements, ensuring real results.
And accepting that measurement isn't gentle, it's invasive, it forces a choice, and it creates uncertainty because key properties represented by non-commuting operators just can't be simultaneously known.
And then the capstone, entanglement, where the whole system is precisely defined, yet the parts are individually indefinite, bound by these spooky correlations that are stronger than anything classical, but still don't break the cosmic speed limit for communication.
Which leads us to a final thought, something provocative stemming from Bell's theorem, which gets a mention in the context of simulating QM.
Yeah, Bell's theorem is fascinating. It's often discussed in terms of ruling out certain types of hidden variable theories, but it also tells us something profound about simulation.
What's the connection?
Bell proved, essentially, that if you wanted to write a computer program based on purely classical, local rules, no spooky connections to simulate the results of measurements on entangled particles like Alice's and Bob's, you just couldn't do it.
A classical simulation can't reproduce the quantum correlations.
Not if it's purely local. To match the quantum results, any classical simulation must build in some kind of instantaneous, faster-than-light connection between the simulated Alice and Bob.
Yeah.
It would need a non-local hidden wire in the code.
So QM itself prevents faster-than-light signaling in the real world. But any classical attempt to mimic QM's results must use non-local communication internally.
Exactly. So the question to leave you with is, if our universe is governed by quantum mechanics, and its correlations cannot be replicated by any local classical model, What does that impossibility tell us about the fundamental nature of reality itself?
Hmm?
Does it hint that reality is, in some deep way we don't fully grasp intuitively, fundamentally non-local?
What is the math showing us that our everyday experience just can't prepare us for? Something to really chew on.